Hello everyone, my name is Greg Ristabin. I'd like to welcome you all today to this webinar titled Improved Method for the Inspection of Fastener Holes Using the NORTEC 600. This Olympus webinar is an introduction and overview to the fastener hole inspection solution in aerospace applications using the NORTEC 600 eddy current flaw detector. Our presenter today is Tommy Bourgeois. Tommy is the product manager for Olympus eddy current testing and bond testing lines of products and has worked for Olympus for about 15 years. This informational webinar will last approximately 1 hour. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the presentation. The chat panel is not used. If we are not able to get to your questions during the webinar, they will be addressed personally either by email or by phone after the event. Now, without further ado, I'd like to turn the presentation over to Tommy Bourgeois. Tommy, take it away.
All right. Thank you, Greg. Well, hello, everybody, and welcome to this webinar for the afternoon session, and thank you for attending. So, as Greg said, this webinar is about improved fastener hole solution by Olympus, obviously based on the new NORTEC 600 eddy current flaw detector. This is applicable in aerospace industry, very much employed. It's applicable to all types of fastener holes, whether it's rivets, bolts, rods, mechanical units, and others, regardless of the material or metal, I would say. It has to be conductive. It cannot be, well, non-conductive because eddy current would simply not work. On some instances, not only holes can be inspected, but some radiuses can also be inspected with those rotary scanner probes. So today we will have a brief introduction as far as a bit of intro on how the bolt hole is beneficial to the industry. We'll see the benefits of this solution, and we will see in detail the features that made the NORTEC 600 a very interesting solution or product for bolt hole inspection or fastener hole inspection. And at the end, we'll see a live demonstration of the NORTEC screen. So, why inspecting fastener holes? Well, I don't think that's new to anybody listening, but the majority of aircraft in service today are manufactured using aluminum as primary structure. Well, all those skins are fastened together using aluminum rivets, not only the skins, but the structures and the units, a lot of things. Rivets being installed by cold working processes and smashing the rivets or bolting parts together, eventually to the aircraft skin. So, obviously, the insertion of rivets in particular does stress the rivet themselves and the skin around it, creating high areas of areas of high stress, which can be seen in red on those simulated pictures. It's same as during the flight cycles. After a number of cycles with basically repeated load on specific areas around fasteners, those skins will eventually develop cracks, which can be detected by this eddy current method. So, the eddy current test, we call that the rotary fastener hole inspection. Often you'll hear me say bolt hole inspection. I guess during the everyday work we refer to it as bolt hole. But obviously does not only inspect bolt holes, but rivet holes and all kinds of holes. So the first component is the probe itself, which can be seen. I hope you can see my laser pointer here on this webinar, but that probe revolves or rotates inside the hole to be inspected. And this is also powered by a rotary scanner. Here's the example with the minimize scanner. It's used to rotate the probe and also sends the data to the instrument. The instrument drives that rotary scanner, which is basically just an electrical motor and a couple electronic components. And inside the instrument, we can see an impedance plane and sometimes a strip chart, or often, I would say, a strip chart display. So, benefits of eddy current fastener hole inspection. Eddy current allows to preserve the integrity of the part being inspected for the simple reason there are no chemicals involved, nothing gets in the way, or nothing basically can alter the chemical composition or has to dry or will cause corrosion. No paint has to be removed. A lot of reasons made the eddy current ideal to preserve the integrity of the part. It's also a very rapid inspection and can be configured as a go-no-go, fairly simple accept or reject based on the impedance plane signal. However, there are challenges in doing that inspection. I'm going to more or less read the text here. Basically, as the aircraft come for service, their fasteners are removed and inspected, looking for cracks that might be occurring from the fastener holes or in the transverse seams. So during the removal of those fasteners, there's a lot of various damages that can occur into the hole itself. While that damage might not be detrimental to the life of the aircraft, it can certainly generate quite a bit of noise or unwanted signal on the eddy current. So we call them variables affecting eddy current inspection. Well, mechanical damage, let's say some threading, some scratches being done as the fasteners are getting removed. Embedded foreign material, whether it's from the installation or occurs during the removal of the fasteners, and additional probe liftoff, which is caused by vibration, can also be observed. So the mechanical damage and all the embedded foreign material, additional liftoff, will have an effect on the impedance plane. However, they can be interpreted from the impedance plane of the instrument, which is the news. The filters, typically there's a high-pass and low-pass filter on the instrument. They are key to facilitate the signal interpretation. And generally speaking, those filters are not that well understood, and also different operators or operators using different equipment can have different results on the same part or on the same calibration specimen. So tuning the filters is always a bit tricky. Moreover, when changing the rotation speed of the scanner, one would need to readjust the filters to make sure that the band of frequencies allowed remains acceptable or allows the test to be made. So, the advantages of the NORTEC 600 fastener hole inspection solution. First of all, and I will talk quite a bit about it, it has application-specific menu. Basically, it's presets that speed up the parameter selection. There are some filter adjustment possible. However, for the most common everyday use, the filters adjustment are not needed. They can be adjusted, but it's just not needed for most of the cases. The results are consistent regardless of the operator performing the inspection. There's a new link function that allows to basically does adjust the filters according to the scan RPM or rotation speed of the scanner. Finally, we will learn about feeder 6 and feeder 8. Basically, the NORTEC 600 features those two signal shapes, and that contributes to satisfy all aircraft manufacturer requirements. So this is a snapshot from the NORTEC 600 brochure. It's rugged and field ready, has a fantastic display, one of the best, if not the best in the industry. Has intuitive interface with the application presets. The buttons or menu operation on this machine are extremely intuitive and easy to use. It also has a complete archiving and reporting solution thanks to the PC software that's shipped with the unit. And to please European customers or those that need to follow the ISO standard, this NORTEC 600 is actually compatible with the EN or ISO 15548 standard. So I don't want to spend too much time on that slide. Just to point out the good features that made the NORTEC 600 an ideal equipment for fastener hole inspection. Well, first of all, it's IP66. IP67 would be totally sealed. The NORTEC 600 is totally sealed up to the knob. Basically, it's not entirely watertight, but it's probably the highest IP rating found on the industry on those equipment. It's very, it's sealed to dust, it's sealed to rain. The only thing you cannot do with it is immerse it in water. It has a long battery life. With scanners, it's 6 to 8 hours, depending on the load and the diameter and probably many mechanical parameters. However, without scanner in normal operation, it's up to 10 and almost 11 hours. The filters have been improved, as we will see in detail. The interface is very intuitive, very easy to use. It has application presets. We will also see that. And there's also a new gadget called the real-time readings. As much as a gadget it might appear, it's actually very handy when it comes to interpreting fastener hole inspection signals. So let's go in the meat of this presentation. Really is to display the key features, the real improvements that made this solution an improvement for fastener hole inspection. So number one, application presets. When you power up the NORTEC the first time or at your demand, you can access this menu. It's called application presets. Those are basically factory presets that will tell all kinds of settings for all the common eddy current applications, including the fastener hole inspection. It saves the user from a lot of steps because, well, everything's preset pretty much. And also allows to instantly configure for fastener hole inspection. As you will see during the live demonstration, it takes only 4 or 5 steps before I get to the end results. And within a minute or so, I can get a calibration done, starting from scratch. So what's preset actually is all the display modes, the synchronization, the speed, the high pass and low pass filters, the eddy current settings, frequency, probe drive, all that. The alarms, if you need them, they're preset. If you don't like them, you just turn them off. It's faster than adjusting the box if you need it. The readings, all that is preset. And pretty much the only thing you would need to adjust is the frequency, liftoff, gains, and, well, and then you would have instantaneous results just like that split screen. So, filters. This section is the biggest of this presentation. There's been a lot of improvements to the filters. And basically, the filter system of the NORTEC 600 is entirely digital. Well, yeah, it does preset values. It has constant shape filters, figure 6, figure 8. We will see what it means. It also has a new link function. We will also see that later. And again, virtually no need to adjust the filters. Well, you can still adjust the filters, and you might still want to adjust the filters in extreme cases. Let's say if you're inspecting 3 inches diameter, which is 76 millimeter hole, well, maybe the filters might need some tuning, but for the bulk of the work and the most of the time, basically, you would not need to adjust those filters. So, you may ask, all right, what is constant shape? What is figure 6? What's figure 8? The link function, and what exactly does the filter to help me? So, here's some further details. The explanation starts with the probe. So we have to know a bit of the probe construction in order to understand the rest. Without going in too much detail, really, that probe is basically rotating in fastener hole, whether it's a plastic probe, it's expandable, it's stainless, or stainless expandable. They all do the same job pretty much. They rotate from 600 RPM to 3,000, 1,500 RPM being a very common speed where POD or probability of detection studies are made. The coil itself is a differential, we call that split D probe. It's basically reflection. There's a driver around two pickup coils that are next to each other, and they are making a differential probe. That probe is actually highly sensitive to surface tracking inside the fastener hole, and it's a differential coil in nature. So a differential coil will provide a differential signal, and that's basically the root of the figure 8. So we call that figure 8 because it creates an 8 figure from the eddy trend signals, basically. And the reason why it's an 8, it's simply when the track hits the coils, it hits one coil before the other, and then because of that reason, it creates one loop before the other. So the eddy trend rotary probes deliver differential signals. We just saw that. The eddy trend signal is affected by mechanical damage, embedded foreign material, additional liftoff and vibration. And the instrument filters aim to improve on signal quality. Basically, one of the main purposes of filters is reducing the strong noise or the strong rotation noise, basically the noise that comes from the test itself. Also, one of the use of the filter is smooth up the signal shape for an easier analysis. And finally, we basically try to achieve a clearer signal for easier interpretation. So, the high pass. The high pass, I told there's a high pass and there's a low pass in the settings. The high pass is the most important. That's the filter that does most of the cleaning up of the signals, basically. The high pass filter aims to reduce strong rotation noise or vibration or liftoff. If I use this example here, imagine aluminum, it's a standard aluminum standard scan at 500 kilohertz. It's a 6 millimeter hole. The speed of the scanner is 1500 RPM. The low pass is off or wideband because a low pass can never be totally off. So if I have no high pass, basically it's pretty noisy signal, and we can see in the background, this is obviously the track signal, and this is the probe motion or rotation or vibration noise. And actually, it's not too bad because it's on a standard. Imagine in the real hole when it gets noisy and a lot of indications occur. So as we increase the high pass to 25, 50, 75, up to 125 hertz, basically the probe is kept at the same position all the time and rotating. So we can see that background signal here becomes smaller as we increase the high pass filter. Up to a point where it gets ideal, there's almost no vibration left. There's quite enough of the track signal. And if we keep increasing the high pass, we basically don't gain anything because it starts to decrease the amplitude of the track signal, and we don't gain much in signal to noise ratio after a while. So we will, for that reason, we will tell that the high pass of 125 hertz in that specific condition is actually ideal. All right, let's go to the low pass now. The low pass, the purpose of the low pass is to clean up the signal, make it smoother so the signal looks better and easier to do analysis. So basically, the same example, now if we operate with the high pass being tuned at 125, so that's the same screenshot as before. Now if I activate the low pass, 1500 hertz, pretty much no effect. 800, there start to be a small effect. 600 down to 400. At 400, the signal becomes very sharp, very straight also, so very easy to interpret. So as I lower the low pass again, the signal remains the same but just gets smaller. So again, after a while, we don't gain much by lowering that low pass. So the sweet, oops, I'm sorry, I touched anyway. The sweet spot would be the 400 hertz low pass here, because we get the best signal without starting to lose amplitude. Okay, So the high-pass filter and low-pass filter operate together as a bandpass. The filters are quite necessary to allow easy signal interpretation. So if we compare the original screenshot, no filters, to high and low pass filters being properly adjusted, there's quite a bit of difference, and it's quite easier to see that signal here than it is without any filtering. So what about figure 6 and figure 8? Well, before the NORTEC 600 with its digital filters, the eddy trend instruments were employing mostly analog filters, and analog filters are made of resistors and capacitors for the most. Basically, different filter settings would also produce variation in signal shape due to the phase distortion from analog filters. So basically, the same instrument would deliver a figure 6 up to a figure 8 depending on the high pass settings. So yeah, the distortion comes mainly from the high pass, and that might raise some questions. So I'm talking about distortion. Well, the figure 8 is a relatively not distorted signal. That's the source or native signal from the probe. The actual high-pass filter, when tuned properly, we can actually obtain a figure 6 looking signal. Well, it's a reverted 6 on aluminum. It would be a non-inverted 6 on steel. But anyway, it looks like a 6, and that signal actually has quite a lot of advantages that we will see later on, but it's basically, it was achieved in analog equipment by proper tuning of the high-pass filter, and that's caused by some distortion from the phase caused by the analog filters that is exploited. So which one is better? Well, they both work, which is good news. The figure 6, however, has an advantage because it visually points to where the signal phase is, whereas the figure 8 offers two possibilities. So this is figure 8 with the strip chart or sweep and the impedance. So can you tell me whether it's 45 degrees or 225? If you would just be looking at the impedance plane, I think it would be fair to say that both are good answers. However, by looking at the strip chart or sweep, we can tell because one of the loops will be occurring before the other loop. So depending if that figure is up or down or inverted, we can tell which one is first, but it needs quite a lot of practice to say that. But with the figure 6, actually, the signal points to where the angle is, so there's no questioning. It's a very clear phase indication. Without any hesitation, I can tell this is a 45-degree or so signal. So, all right, you may say, I can see the phase easier, but what's the advantage if I'm going to inspect those holes? The phase actually indicates a lot about the indications, I would say, whether they are genuine or false indications. So genuine indications will point to specific angles, and that's all because of eddy trend 101, eddy trend theory, that predicts that basically surface cracks will have a certain angle, liftoff will have another angle, subsurface might have another angle, inclusions will also react differently. So all kind of variables will react differently to the eddy trend test. And that's not new or specific with that application. It's just the physics of eddy trend testing. So non-relevant indications such as surface scratches, shavings will also point to other angles than the genuine defects. It's not impossible to do that with the figure 8. Do that, I mean separate the indications, genuine from false. It's just a lot easier with figure 6. So here are real examples. That example was taken from actually an old 1958 aircraft that's still flying today. Actually, they pulled apart from service and removed fasteners. So on several holes, we had mechanical damage from the threads. Okay, a pretty thick layer actually. As you can imagine, a 58 aircraft was not very thin back then. So the actual indications we found were not at all pointing to the same phase as the non-relevant indications. So the NORTEC 600 features that real-time reading here pointing to 109 degrees, and the genuine track was 51. Next page, still aluminum, the same, some other holes from the same part. Some surface scratches, just a different pattern that we observed, and another track here that points pretty much to the 50-ish degrees, and the non-relevant indication is in the 100 degrees. On steel or ferromagnetic materials, well, steel is generally speaking a bit harder to interpret just because it's a noisier material to inspect. However, it still has this, because of physics again, has the advantage that cracks and non-relevant indications are even further separated than on aluminum. So here's some, consider the liftoff was set horizontal, and there's light damage on this one, very light scratches, and there's a genuine track. There's almost 90-degree difference between both, 130 degrees for a real track and 20 degrees, that's 100 degrees difference. So another example with thread marks. I hope you can see that blue image on from your location. It's basically a horizontal signal, just like liftoff would give, and the real track is actually 120 degrees. That one was a fairly large track. So that's actually, again, quite a lot of difference. So the figure 6 helps a lot to identify the signal polarity because there's only one extrusion of the signal to consider and not two. So it helps to identify those flaws. And the NORTEC 600 features the new real-time readings that displays the live signal angle. Basically, that number appears live, and we will see it during the demonstration. So there's also the constant shape or constant signal shape filters, and there's a patent in progress on that. Basically, that allows to keep the figure 6 or 8 regardless of the value of the filter. So if you light figure 6 for an application, you will never lose it depending on the filters. If you wish to tune the filters, because it's constant shape. It's always tuned to a figure 6, which was pretty much impossible to do with the analog equipment back then. It seems a long ago, but really wasn't. And basically, it's not entirely impossible. It just would have needed so much a big circuit to perform that. So it's also, the NORTEC 600 is also switchable between figure 6 and figure 8. There's an instant control, and I'll try to demonstrate that later on. So you might ask, how about if I change the rotation? What happens to my feathers? Actually, a very good question that we get frequently. The new link function answers that. So it will adjust the high pass and the low pass according to the rotation speed. So you can still change your filters as needed. However, the link will track the rotation speed and adjust those filters. The advantage is when the link is on, it will ensure that the signal remains constant through the entire RPM range. So here's 3 examples. Let's say we calibrate at 600 RPM, very low speed, high pass 50 Hertz, low pass 160. Now we increase to 1500 RPM. So the link will automatically adjust those filters, and I hope you can see the signal, but there's basically no difference between the two because the filters are properly set in both cases by the link function. Even if we stretch to 3000 RPM, the high pass and the low pass get adjusted and the signal remains the same. The only difference I can tell at least is that the 3000 RPM might be noisier because there's more vibration at higher speeds, but that's pretty much it. So another improvement that the NORTEC 600 brings is obviously it does support the Olympus scanners, and we currently offer 3. There's a Minimite general purpose scanner, There's the RA2000, which is useful for tight axis. It has a smaller footprint. And the Spitfire is a gun-looking scanner. It has more torque for larger diameter holes. We didn't stop there. We also made the NORTEC 600 compatible with the most popular competition scanners out there, perhaps the GE or Hawking mini drives. There's two recent versions that are supported. Roman MR3, and we're working on some more. One of the last improvements that are applicable to bolt hole or fastener hole inspection is complete archiving and reporting that comes with the NORTEC 600. Basically, you can save files instantly. Up to 500 files can be saved on the micro SD cards of the instrument. The programs or setups and data files are actually merged into single files. So I don't know how many times I've heard comment about hey, I thought I saved my file, but I can't find it because somebody saved the data file and thought they saved the program, or the opposite. So that's not happening anymore because there's only one file directory, and each file saves both the data and the program inside. There's also an onboard file preview inside the instrument. So using the knob, you can navigate through the files, you can recall, you can set as reference, and you can hide or show those readings as you wish. So thanks to the NORTEC PC software, the complete archiving and reporting is very easy. 3 steps, basically save all the files you want. Then you connect to the USB port and import those files in NORTEC PC. The NORTEC PC software is fairly intuitive, and then you can press, there's export all files as PDF and produce basically from a single click. That's interesting. Even though you had 200 files, you still press a single click and you obtain 200 separate PDFs for each of the files that you recorded, and then you can easily archive that to suit your workflow. So it seems we have reached the live demonstration of the instrument. So I'm going to switch to basically a VGA capture device that allows to see the screen. Unfortunately, you can't see what I'm doing. I'll try to describe as I go, and you cannot also see the buttons that I'm pushing. But when necessary, I'll try to make that clear. So basically, the instrument right now, as it is, it's configured for surface. So it's not a fastener hole inspection application. It's just a plain impedance plane using the outdoors color scheme. So right now, I'm connecting the Minimite. I actually did connect the Minimite, so it's recognizing it thanks to the PowerLink technology. So I press Continue, and then I get into an optional menu that actually I will use because I highly recommend you use it if you play with the NORTEC 600, and that's the application presets. Basically, the interface suggests me to use it, so I will press OK. And then I get into a preset screen with preset alarms, preset parameters. So 500 kilohertz angle, gains, everything was preset, so it works from the start. So let's see that. Now I have an aluminum standard, okay, so I'm going to null the probe. Now I just start the scanner. You might actually hear it rotating. And let's do the step. Well, if application selection was step number 1, let's do step number 2, which is adjusting the liftoff. So right now I'm setting my probe to barely touch or graze the surface, and then I press the angle key and adjust the angle with the knob. So I'm trying to put my liftoff as horizontal as possible, and because the system defaults to figure 6, that means 180 degrees reading. So next step, the track. Now I'm going into the track signal, okay? So I need to adjust the sensitivity or gains. So I press gains. I'll just make sure that I don't exceed the 10% mark here, horizontal, and then I'll increase my vertical gain. until I have proper detection. And I'm pretty much done. I would be ready to inspect right away. And then the rest I'm going to show you is just options or other features. So while I'm maintaining this probe rotating, I want to show you that I can change my sync angle, okay, and I can delay this sweep signal. And then we can change the filters and all that nice stuff. So if I go to filters, we can see the filters. And I talked to you about the scan RPM and the link function. So right now the link defaults to on. So let's see what happens when I actually lower the speed. As you could see, I hope the filters were actually tuned and changed from the rotation speed. But the signal always stayed the same. Even though I increased to 3000 RPM, basically, as long as I maintain the probe at the same spot, the signal remains the same all the time. And even though I try to slow down the probe with my fingers, so I'm increasing the friction, you can see the speed change from the strip chart. Basically, the motor or the NORTEC will compensate for the speed and try to adjust the speed always constant. So once you're happy about that, you can press the full screen key and get to the instant full screen menu or display. The real-time readings, as can be seen at the bottom, in particular, it basically shows the angle. So if I go on a good hole, there's nothing really to report, so nothing interesting. As soon as there's an indication, we can see the angle. So right now it says 49 or so degrees. Here's another track, 46. So that's a live, it's called a real-time readings, and it's a live measurement of the phase angle. So the top reading actually says there's more option, but it says VPP, that's not voltage, but vertical peak to peak. It's basically how high the signal spreads over the vertical axis, and the unit is divisions. So right now we can see almost 5 divisions on top and 2 and almost 3 on the bottom, so it's a total of almost 8 divisions. So in a nutshell, that's the really the edit trend features that are immediately applicable to rotary fastener inspection. I can also change the displays, go to a pure impedance plane, and basically I could freeze my display. Nothing prevents me from adjusting the angle a little bit better, because we have this new feature on the NORTEC that's called a calibration from frozen signal. So right now I can tune my angle to be a little bit better adjusted. So as I unfreeze the equipment, I will just get better signal. Okay, so sweep and impedance was the default. We also have sweep only, and then I can change my grid. There's off, 10 by 10, fine grid, coarse, okay. And there's also a waterfall display. So waterfall, I can make that a bit longer and set some auto erase on the waterfall. So basically, as I scan the entire hole, I can have some waterfall data, and it's also possible to do it in full screen mode. Anyway. Well, so the last demonstration I would like to do is using a steel reference standard, just to show you how easy it is and what sort of results you can have from the steel. Actually, it makes me think that I did not show you the figure 8, so I'm sorry about that. Let's go back to special menu, and I absolutely need to show you that figure 8 thing. So right now the default is figure 6. I can go here, change it to figure 8, and for engine inspection, for instance, we would have instant constant figure 8 throughout the filters range. Okay. All right, back to what I wanted to show you, all those parameters. So I'm sorry, I need to go to application section. I will again recall the bolt hole inspection just to default the system. I just press null, and I'm pretty much ready to inspect that, to calibrate on that steel. So the difference with the steel is out, we'll have to employ less gain. So let's lower the gain already. And then I'll adjust the angle the same way. So the lift off goes to the right, or 180 degrees. And then I should be able to basically adjust that signal. So that's the track indication. Okay. So horizontal gain may be a bit less. I guess that would do it. And then full screen. And now I have a perfect figure 6 for steel hole inspection. So that quite concludes the live demonstration of the equipment of the NORTEC 600 instrument configured for fastener hole inspection. So again, I want to thank you about attending this for attending this webinar. Please remember to check the website for various videos that we have, product manuals, also how to set up instruction videos. And this webinar will also be archived and available from the library of webinars, so it can be watched over and over again. And here's the last propaganda part on this video. And just to say, don't forget to check out the new Bondmaster 600 composite bond tester, multi-mode, very powerful instrument actually. So again, on behalf of